Hello class, welcome to lesson 9.6, which is all about exponential growth. By the end of this lesson, you should be able to graph exponential functions, and you should be able to identify behavior that displays exponential behavior. So let's look at what is an exponential function. So an exponential function is a function that can be described by an equation of the form y equals a times b to the x power. Okay? A can never equal 0 because that would just end up being 0 times the number, and we don't want 0 times the number. Okay? So A has to be a number. It can be positive or negative, and B has to be greater than 0, but it also cannot be the number 1. Because if we take 1 to, it doesn't matter what power. If we did 12, that's still 1. If we did 1 to the third, that's still 1. 1 to the negative third, still 1. Okay? So we can't have b equal 1 because then we'll just end up with y equals a times 1. We don't want that. We want the numbers to change. So some examples, y equals 2 and then times 3 to the x power. So in this instance, my a value is 2. My b value is 3. And then I keep changing the x value by plugging in random numbers. So I would pick maybe 1. I'd plug 1 in. I could plug 2 in and see what numbers I get out. Okay. Some other examples, y equals 4 to the x power. So my a value would be 1 because there's no number in front, and b would be 4. And then same for this, my a would be 1, my b would be 1/2. Okay. Let's, actually, one last thing. The way these exponential functions look when you graph them, you're going to have things that look like this, okay? Or sometimes you'll have things that start low and then get higher, okay? That is what our exponential graphs look like, instead of those parabolas that we were doing earlier this chapter. Okay, so we're moving away from the parabola and talking about exponential functions today. So let's look at our very first function. We have graph y equals x to the fourth, and graph y equals 4 to the x power. We want to find the y-intercept, and we want to state the domain and range. So what we're going to do, what I'm going to tell you guys to start off with, is make an XY table, okay? So do some maybe negative numbers, some positive. So if I do a -1, I'm going to write out the function for you guys as well. I'm going to make the fancier XY table. Okay, so then I have 4 to the x, so that's 4 to the negative first power. And on your calculator, that's where you do 4, you hit your caret key, and then you're going to want to use some parentheses and do a -1. Okay? And if you plug that in, you're going to get a decimal of 0.25 or 1/4. And then let's plug in 0. If I do 4 to the 0 power, remember, anything to the 0 power is the number 1. If I plug in a positive 1, I have 4 to the first power, which is just 4. If I plug in 2, I have 4 to the second power, which 4 to the second power, or 4 squared, is 16. Okay? So then I would go and I would plot these points, but I want to know what my y-intercept is going to be. So remember, the y-intercept is where it crosses the y-axis, so it's when x equals 0. So when I plugged 0 into my equation, I plugged 0 in for x, I got a 1 out. So my y-intercept occurs at 1. My domain is going to be really similar to my parabola. By similar, I mean it's the same, where you say all real numbers. You can plug in any number for x and you'll get a value out for y. So that's why the domain, it doesn't matter what number you plug in, you'll get a number out. the range, the numbers that we get out, now those are different. If you look at it, our smallest number here is a 1/4. If we plugged a -2 in, we would have 4 to the -2nd power, which if you plug that in, is the fraction 1/16. So we're getting closer to 0. We're getting smaller. But with exponential functions, your range is typically going to be greater than 0. Okay. Later on, you'll see graphs that are a bit more challenging. This will change. It won't always be y is greater than 0. But for now, that's going to be kind of our standard. Okay. So if I want to graph it, I can just plot those points. Okay. So to save some time, I have those already plotted for us. So if we look over to the right, you can see the graph y equals 4x. You can see that there is -1, 1/4, there is 0, 1, 1/4, and then 2/16 is way up there. Okay, so now I want to use this graph to approximate the value of when x equals 1.5. So I'm going to go over 1.5 is right about there. So I'm going to just kind of do a dotted line and see when does it kind of hit. So if I look, I'm at 1, 2, 3, 4, 5, 6, 7, 8. So if I do y equals 4 to the 1.5, that is about 8. Or if I actually plug that into my calculator, hit 4, hit the caret key, parentheses 1.5, you will get out the number 1, or you'll get out the number 8, okay? So that is how you do that. Start by making an XY table. Make sure to plug 0 in for x. That way you get a y-intercept. And then state your domain and range. Remember, domain is typically all real numbers. Your range is typically going to be y is greater than 0. All right, so which one of these is an accurate graph for y equals 5x? Hopefully you decided graph B was what the graph y equals 5x would look like. Go ahead and try one more. Hopefully you got about 1.5. So if you do 5 to the 0.25 value, you get 1.5. All right, let's talk about example 2. We have graph y equals 1/4 x. Okay, so again, I'm going to make an xy table. So I say x, my function is 1/4 to the x power, and then y. So if I plug in a -1, 1/4 to the -1 power is 4. If I plug 0 in, 1/4 to the 0 power is 1. And if I have 1, I have 1/4 to the first power, that is just 1/4. Okay, so let's look. My y-intercept is when you plug 0 into your function. So my y-intercept, again, is 1. My domain, it doesn't matter what numbers I plug in, I will always get a number out, so I can say all real numbers. And my range, if I look, again, this time my higher numbers are my negatives, my lower numbers are my positives. When I plugged a +1 in, I got a 1/4. When I plugged a -1 in, I got a 4. So my range, though, is still positive numbers. It's y is greater than 0. If you're too lazy to write all real numbers, the symbol for all real numbers is an R with 2 lines on the left-hand side, okay? That symbol means all real numbers. So if you don't want to write out all real numbers, you can use that symbol. All right, and then once you plot those points, you should get a graph that looks like this. And we want to use this graph to approximate the value when x equals negative 1.5. I'm going to go negative 1, negative 1.5 is right about there. And when I plug that in, it crosses at 1, 2, 3, 4, 5, 6, 7. Let's see, 1, 2, 3, 4, 5, 6, 7. Crosses somewhere between 7 and 8. My line's not perfect. But if you wanted the precise, all you have to do is say 1/4 to the negative 1.5 power. And when you plug that in, you get 8. Alright, so basically the same thing as before. The only difference, if you look, the higher numbers, like I pointed out, are on the left side, whereas before, our higher numbers were on the right side. Okay. The way to tell if you have an A value of 0 to 1, you have something that looks like, or sorry, a B value. That should be B. If you have a B value between 0 and 1, so if you have a fraction, your graph looks like this. If you have a B value, so like in the last example, our B value was greater than 1 because it was a 4, you have something that is increasing, okay? So here we had our 1/4 to the x, and here we had our 4 to the x, okay? So that's the difference. It's the same graph, but it's flipped. All right, go ahead and figure out which graph best represents 1/8 to the x power. Hopefully you decided graph A would be a good example. Try another one with this second graph. Hopefully you said the approximate value is about 2. If you have questions, be sure to reach out to either myself or a friend for some help. All right, example 3. Some people say that the value of a new car decreases as soon as it is driven off the dealer's lot. The function v equals 25,000 times 0.82t models the depreciation of the value of a new car that originally cost $25,000. V represents the value of the car, and T represents time. And T represents time in years from the time the car was purchased. Graph the function and what is the values of V and T. Which values of V and T are meaningful to the function. So I already have it graphed out just to save time. And so this is what the graph kind of looks like. When we start, the value is way up here. It's $25,000. And as time goes on, you can see that the price of the car, the resale, is going down. Okay, makes sense, right? What values of V and T are meaningful? What that's asking is basically a fancy way of saying what's your domain and range. So for value, we know that it's for sure less than $25,000, right? But it's also equal to that $25,000 because that's what someone paid for it. That's what it originally is at the lot. So it has to be less than $25,000. But also, it doesn't make sense to be less than 0, right? The value has to be something more than 0 because otherwise you're paying for your car. We're not talking like car payments, okay? We're saying that your car is so bad you have to keep paying just to drive it, which is not what we're talking about. Okay? So the value of your car is somewhere between 0 and $25,000. So that's what it's asking for in this last question. Now we want to look at time. Okay? Now for time, the only thing that makes sense, because we can't go back in time, is it has to be greater than or equal to 0. Okay? Time starts when that car is purchased, and then you can't go back in time. So that is that. And then once we look at the next question, what is the value of the car after 5 years? Well, if we look, value of the car after 5 years, we have 1, 2, 3, 4, 5. So if we go up, it's somewhere in there, and somewhere over there. And our scale is by $5,000. So here's 5,000, 10,000, 15, 20, and 25. So the car is somewhere around $10,000. But I want to know exact. So this is where you take that equation, that 25,000 times 0.82, and you plug in 5. So on your calculator, what that would look like is, what I would do is I would take 0.82, I would do an extra parentheses, and then do your caret key, type in 5, close the parentheses, so that way that fifth power is only applied to that 0.82. Hit your multiplication, and then type in 25,000. Okay, that way you can type everything in all at once. And if you do that, you find out that the price of the car using that equation is $9,268.50. So 10,000 is close, but if you thought you were getting 10,000 and then you only got this much, you might be a little sad. So it's nice to use the equation to find out exactly. And go ahead and look at these graphs and see which graph matches the function. Hopefully you said letter D. If you have questions, let me know. And then go ahead and look at part B. Hopefully here you ended up with $18,040. If you have questions, be sure to reach out for some help. All right, we're moving on to our last example. We want to determine whether the set of data displays exponential behavior. Okay, so before we're looking at the graph, like what it physically looks like, let's talk about the XY table. We want to explain whether or not this is an exponential function. So if we look at our XY tables, we always want to look, how are they changing? So here our X, we added 10, we added 10, and we added 10. Our Y, how do we get from 10 to 25? Well, we could either say we added 15, and then we can look at how much did we have to add each time. But I can tell already that 25 plus 15 doesn't give me 62.5. So I know that's not what I'm looking for. I'm not looking for subtraction. So addition and subtraction are ruled out. Going from 10 to 25, I know I'm not dividing, because if I was dividing 10 by something, it'd be getting smaller. So I know I'm multiplying. So I just have to figure out how much do I multiply to get from 10 to 25. Well, I multiply by 2.5. Okay, so if I take 25 and I multiply by 2.5, do I get 62.5? Yes. And if I test the next one, 65 times 2.5, that gets me to 156.25. Okay? I know that these are all changing by the same amount. And if you're unsure of how to tell, like what you're multiplying by, start on the right-hand side and divide by the number to the left of it. If you do 156.25 divided by 62.5, you're told what that number is. And then if you do 62.5 divided by 25, that equals 2.5. Okay, so if you're ever unsure of what you're multiplying by, just take the number from before, or the number on the right, and divide it by the number to the left of it. Okay, because sometimes it's not an obvious thing. But we want to go through and we want to state our domain and our range and explain whether or not this is exponential. Well, our domain, our x values, are changing at a constant rate, which is good. We need that. Wow, my handwriting's getting really bad. Sorry, guys. And then the range is multiplying by a common positive factor. Okay, so that's how my domain and range are behaving right now. So since we know that my domain and range are changing at a constant rate or multiplying by a common positive factor, I can say that this function is exponential, and I can actually write a generic formula for it. I can say y equals, I don't know what my a value is yet, but I know that since my range changes by 2.5, I'm going to put a 2.5 there, then I'm going to use x. So that's how you would start to write an equation based on the table. We're going to look more in depth with that later on in this chapter, but that's how you'd write an equation for it. Okay? Why don't you go ahead and see if you can determine whether the set of data displays exponential behavior. Remember, you need your x to change constant rate. You need your range to be multiplying or dividing by the same amount each time. Hopefully you determined, yes, this is an example of exponential behavior. Okay? If you have any questions at all, please do not hesitate to reach out for some help. I'm more than happy to help you. Have a great day.